Chapter 11, Rolling Torque and Angular Momentum. So as a quick reminder before we dig into it, I have office hours on Zoom during these times. And so if you click on the link to the Zoom page, that'll take you to my meeting, and we can chat. Stem cell tutoring is also on Zoom, so I encourage you to click over and check them out. That's another great resource for you. Right, so chapter 11 is in many ways an expansion of chapter 10. We're going to see some similar ideas. The main new one will be our angular momentum. So we're finally getting to that, which is quite a relief. But first, we're going to take a look at rolling. And the big idea here is actually what's in the title. So in section 11.1, rolling as translation and rotation combined. So smooth rolling can be a combination of translation, which is shown with this yellow light in the middle of the rolling object here, and the red light, which is highlighting the rim. And the path that the red light takes is actually known as a cycloid. So that's an interesting aside there. Okay, so first, we're only going to consider objects that roll smoothly. So we're not going to worry about any slip, but we're going to assume that it's just a nice steady forward roll. Also, with these things, the center of mass, which is just the com of the object, will say moves in a straight line parallel to the surface. That was that yellow light on the previous slide. That, hey, the center of mass, if it is this smooth rolling, will always be moving in that straight line. The object, though, is rotating about the center of mass as it moves. So the rotational motion is defined by basically our linear to angular variable equivalence. So S, the linear distance, is equal to the angular displacement theta times the radius r, which we can see in this figure here. If we imagine a bicycle wheel starting at point P, if it's moving forward, then it will roll out and sweep out some distance. And this is an angular distance, so you could calculate that arc length S with r theta. But if we lay it flat on the ground, that would be that same distance S. So the linear distance is actually the same as the arc length here. Similarly, the center of mass velocity, vcom, which is the speed that it's moving translationally at the middle, is just going to be the angular velocity omega times the radius. That will tell you how fast it is moving in a translational direction. Okay, so if we focus in on that motion of a bicycle wheel, one thing we would see in it is that there is pure rotation. It's like it's spinning in place. And so that means if we're just considering rotation at the middle, it's not moving because everything's moving around that point. At the top, it's moving forward with the center of mass velocity. At the bottom, it's moving backwards with the center of mass velocity. That's what we'd expect for something that's just spinning in place. For pure translation motion, everything is moving forward at the same rate. So if you have a round object, right, it's all just translating together at vcom. Now with rolling motion, it's a combination of the two. So we have to add them together at each point. So if we add them together at the midpoint at O, we have 0 plus vcom. We just get the center of mass velocity at the middle, which matches our previous slide on the picture of what we have going on there. At the top, we have two velocities in the same direction. So it's at the top of the wheel is actually going twice as fast as the middle of the wheel. And this is where it gets really interesting. At the bottom, we have two velocities in opposite directions. So there's actually no velocity at the bottom. The wheel is stationary, which seems really weird. So I hope you sit with that for a moment. Here's a picture that shows how that can be, right? Notice that the bicycle wheel, it's rolling. At the bottom, it's in focus because it's stationary for a split second, versus the top is moving much faster, and so the image is blurry. So a way we could actually picture rolling motion is that the entire wheel is rotating about the point at which it's in contact with the surface. Everything else is rotating around that. So you need to be traveling fastest at the top of the wheel and at a medium speed in the middle of the wheel. And the best way I have to really settle in on this idea and feel okay with it is to imagine a tank. So with the treads of the tank, the bottom treads are not moving along the ground. You can click to a video or look up tank motion and you'll see they are set in the ground, but everything else rotates around them, right, and shifts the treads forward, and then they lay down and they're stationary until they get pulled up and around to be laid stationary again. So a tank is an extreme example of looking at this rolling motion. Let's check a checkpoint. So it says the rear wheel on a clown's bicycle has twice the radius of the front wheel. A, when the bicycle is moving, is the linear speed at the very top of the rear wheel greater than, less than, or the same as that at the very top of the front wheel? And part B is the angular speed of the rear wheel greater than, less than, or the same as that of the front wheel. So I want you to be disciplined here. I want you to think it through, so take a moment and hit pause now. Okay, hoping you did that. So let's now check. So the linear speed of the rear to the front is the same, but the angular speed is less. Why is that? Well, first off, we can picture the linear speed. That means how the bicycles are traveling, and we want the bicycles to be able to stay together, right? So even if the rear wheel is ginormous compared to the front, they're wired together. This is a strange bicycle, but we'll go with it, right? And so the whole bicycle is moving forward at one speed v. So that part has to stay the same for each of them, that linear speed. But the angular speed of the big wheel, notice it doesn't have to rotate very much to cover the same ground as the little wheel has to spin a lot to keep up with the big wheel. So there's less angular speed in the big one, the rear wheel, versus in the front wheel. Right. Let's keep pressing on for now. So section 11.2, forces and kinetic energy of rolling. I'm just gonna keep rolling right on through. So for the kinetic energy of rolling, it's just a combination of the two kinetic energies we've seen already. So we have our kinetic energy of rotation, 1/2 I omega squared, and then also our classic kinetic energy, 1/2 mv squared. The only slight difference here is because we're focused on rolling, we're going to consider its rotation about the center of mass. So the I is the I about the center of mass, or ICOM. And the speed, the translational speed v, is just going to be vcom, the speed due to the translation of the center of mass. So this just says if an object's rolling, it has to be that same combination that we saw in the previous section of translation plus rotation. Now, if a wheel accelerates, its angular speed is changing. So for a wheel, if you're at a stoplight and the light turns green, if you want to accelerate, you need some force so that you don't just burn out, right? If you just step on the gas, you'll feel your wheels, they might start to slip a bit. So in order to create this center of mass acceleration, ACOM, that's equal to the angular acceleration times r, again, that's an equation we saw last chapter, but now applying it here to the linear acceleration, we need a force to prevent your wheel from just sliding against the concrete. So it is a force of static friction, and it's forward because your wheel is trying to slide backward. So because your wheel is trying to push back, the force of friction here is forward, because the force of static friction is always opposing the attempted motion. If there is some slip, then the motion isn't smooth rolling, which is not within our focus. So for smooth rolling down a ramp, this is another specific example. Our gravitational force will be vertically down. Cool, that's something familiar. The normal force will be perpendicular to the ramp. The force of friction here is interestingly going to point up the slope. Why is that? Well, if it started to slide, then the force of friction would be up the slope. And so that upward force is what allows it to instead roll down. So that frictional force is why there's a rotation. If there was no friction, the ball would actually just slide down the ramp. And so interestingly, you know, the forces at the normal force and Fg cosine theta just balance out in the vertical direction. The forces of gravity in the down the ramp, Fg sine of theta, and the force of static friction will determine our linear acceleration. But the key is that the torque that the force of static friction applies determines the angular acceleration, because the force of static friction is the only force that's not acting at the center of mass. And so it's able to create a torque on the ball and cause that rotation. And the book has a lot of details on this derivation. I'm going to skip over them for now and just note that we can use all those equations together. The net force, the net torque is equal to I alpha, to find the acceleration of an object rolling down a ramp. And it's equal to negative g sine theta divided by 1 plus I center of mass, divided by mr squared. This tells you how an object will accelerate if it is rolling down a ramp as opposed to just sliding down a ramp. We notice it's actually very similar to our sliding down a ramp acceleration that we got when we did in lab, week 3 or 4. We saw that the acceleration was just g sine theta. So g sine theta divided by 1 was what we got for sliding. Now that we're rolling, we have this extra term of I divided by mr squared. And that accounts for the additional energy that goes into getting it moving, getting it rotating. And so, you know, you can tell all your friends, your family members, physics. That's how I roll, right? Super cool. Okay, moving right along. Let's look at another checkpoint. Disks A and B are identical and roll across a floor with equal speeds. Then disk A rolls up an incline, reaching a maximum height h, and disk B moves up an incline that is identical, except it is frictionless. Is the maximum height reached by disk B greater than, less than, or equal to h? This is a really interesting one, so I want you to think about it. Please take the time, fight inertia, reach out and hit pause now. Okay, trusting you did that. Let's now take a look. So it's B, the maximum height reached by B, the frictionless case, is less than that reached by A. Why? Well, for A, because there's friction on the ramp, then as it rolls up to the ramp, it's able to keep rolling up the ramp, and all of that rotation is able to convert into translation up the ramp. But for B, as it rolls into the ramp, when it reaches the ramp, it's just spinning. And so it's only the forward translational energy that's able to convert into potential energy while it spins. So it's still spinning at the top, and similar to the bullet block mystery, that means some of that energy just is going into its spinning, not into that potential energy of going up the ramp. Now, this would be very different if they were, say, having to go down the ramp. You could imagine some different scenarios where you'd get a different result. But for this one, since they both start out rolling at equal speeds and then start to go up the ramp, where one has friction, one doesn't, friction actually helps disk A to go to a greater height. So there you have it. Friction can actually be your friend. And that pulls us through to the end of section 11.2.